And let's go back to that. So yesterday's video was about mixing strong acids and strong bases together, and we were looking at whether or not the pH would be neutral, acidic, or basic. So hopefully you've had a chance to look through some of those questions. And I'm going to launch on today's lesson. And today's lesson is mathematically, I find it really is more like Chem 11, really. But I think when I write this word down, students just really get bogged down by the meaning of that word, and it becomes a much harder question. But the math's actually more like Math 11, Chemistry 11 math. Like you remember those ice tables you're doing last chapter? There's nothing like that here. And so what is a titration, I guess? So a titration is an experimental procedure that all of you guys will do if you're going into post-secondary sciences. So if you're doing biology or chemistry classes, I'm guaranteeing you're probably going to do a couple titrations, I'm assuming. And so what a titration is it's an experiment, really. And it's an experiment to find out something you don't know, which is usually why we do experiments. And there's many different types of titrations. There's actually solubility ones, there's acid-base ones, there's redox titrations. And so the term titration refers to a whole bunch of different testing things you could do where you're trying to find out some property of a chemical. So you might be looking for, so try to, draw. Sorry, my computer's all slow here. So try to find like maybe the concentration of an unknown, maybe in this chapter, unknown acid. So maybe you've got this acid, you're trying to find out its concentration. Well, you could do a titration to figure that out. Maybe you're trying to find out the type of chemical. So maybe what you're trying to find out is the chemical that is in a beaker. You're not even sure what the chemical is. You might be trying to find out the molar mass of a chemical. You might be trying to find out how pure a chemical is, the percent purity of a chemical, and the list just goes on and on and on. There's so many things you could do that you could use a titration for. So the question really, what is titration? It's not really a simple answer, other than to say it's a type of a procedure or experiment you would do to find out something you're trying to determine about some chemical that's interested you, basically. So in this chapter, I'm going to really narrow down the types of questions I'm going to ask you, because the book has a lot of different types of titration questions. And because of how we're delivering this form of curriculum, I want to keep it somewhat simple here. But there's a bit of apparatus you need to kind of understand in a titration. And this unfortunately would have been one of the labs we would have worked on here. There's a virtual lab. I'm going to try to see if I can get that up and running. I think Mr. Quast had some success with that. But so here's a scenario. So let's say you have, let's say an example, a beaker has 250 milliliters of HCl. You titrate a 25.0 milliliter sample of the acid using 0.100 molar NaOH. Equivalence is reached when, let's see here, when 35.0 milliliters of base are used. Okay, so I'll give you, you could write that down. The video is going to be posted online, so if you want to just go back to it and look at it. Now, this kind of question, I think when students read it, they're really overwhelmed by the language that's in the question and what they're really being asked to do. But keep in mind that the math you have to do here it's basically Chem 11 math, but the wording can be kind of tricky here. So let's give you an idea what this would even look like in the first place. So we have a long tube, which we call a burette. So normally I would show you this in class. It's basically just a giant long tube. And the long tube has like calibrations on the side. So it tells you the volume that's in there. Okay. And then at the bottom here, there's a little ring there. And there's this thing here. And this thing's, sorry, I'll go back to that, sorry. The burette is full of a chemical that we call the standardized solution. Sometimes it's just referred to as the standard. And what's important about the standardized solution is that this is the chemical that you know the concentration of, like you know what it is and you know its concentration. So basically the standardized solution, you've prepared it beforehand, and so you know the concentration. Now, I deliberately in this example did not ask you to do anything. I just told you stuff. And so we're going to write an end sentence here to show you what you're trying to find out. But based on that information I've given you, do you think the HCl or the NaOH would be the standardized solution? If the standardized solution is the thing you know the concentration of, would it be the acid or the base that should be put in there? Well, in this experiment, you know the concentration of the base itself. You know the molarity of the base, and so we use this chemical to titrate the acid. So we're trying to find out something about this acid. That's why we're doing the experiment. So the question would have probably said to you at the very end here, it would say, find the concentration of the acid. So find out what its concentration is. You could also find out the molar mass if you were asked that, or how many grams of acid you have in there. So lots of different questions that can be asked here. So then what happens is this burette's full of the base, and now what you have is you have a beaker that's below it. And in that beaker is some acid. So this is the HCl then. Now, you'll notice that the question gives you two different volumes for the acid. It says you have 250 milliliters of the acid, HCl, and you titrate 25 milliliter sample of the acid. So why would we give you two different numbers, and why wouldn't you have just titrated the original acid to start with? Well, just a couple of reasons here, or sort of purposes here, is that if you're trying to find the concentration of a chemical, and so you have this beaker and you're like, I want to find out what the concentration of that is. The reason you might want to find that is because you might want to use that chemical. So if you add a whole bunch of base to all of the acid you're trying to find out the concentration of, it makes that useless now. And now you can't use that acid. So if you use a little sample of it, say 25 mils, and you find out the concentration in the sample, well, that would have to be also the concentration in the big beaker. And we use this analogy. I think Noah last week asked about a question on the test where we said that if you were drinking a glass of Coke or a big bottle of Coke, the whole thing, they both would taste like Coke to you. They both would have the same concentration of sugar, but the sample of the acid would have the same concentration as the original acid. So this allows us not to ruin the chemical we might want to work with down the road. We might want to figure out what is the concentration of the acid and go here. So the burette contains the standard. That's the chemical you know the concentration of. And it's got little lines on the side of the burette that allows you to determine the volume of base you add. And we're going to add it to the acid to try to find out what the concentration of the acid is. So this is the sample. So this is the 25 mil sample here. And then there's obviously some bigger beaker somewhere, a bigger jug or something, like big jug, that has like a whole bunch more acid in it. And that's the 250, although you would have taken 25 mils from it, so you would be a bit smaller, I guess, but you still have lots of acid to work with. And of course, the question is, you don't know its concentrations. You don't know what the molarity is of that. So what you do is you add some base to the acid, and eventually you reach this thing called equivalence. And we'll talk about what that means in a second here. But the equivalence is really an important thing to reach. It then allows you to connect these two concepts together. So how do you get the base into the acid itself? Well, there's this little knob at the bottom here, and it's got a great name. It's actually it's like a perfect name for a birth control device. It's called a stopcock. Stopcock. Anyway, so you turn that thing around, and what happens is base starts to drip into the acid here. And basically, that's a good pun. So what happens is you add your base, and the HCl start to neutralize each other, and eventually you get to what's called equivalence point. So we said we're going to define equivalence point now. So equivalence point is basically when the moles just a second here. Let's go check one thing with my calculator here. So the equivalence point is when the moles of H plus equal the moles of OH minus, at least in an acid-base titration. So that's what the word equivalence point means here. So here we go. So how do we work with that? Well, the first thing we should try to do is figure out how many moles we actually added here. So what I'm going to do first here is find out the moles of NaOH. Okay. Now, what I would say is that the only thing that's a bit frustrating about these kinds of questions, you do have to show a lot of work to explain your answer. But when you actually go back and look at the math you did, there's probably two calculations you have to do. So we know to find moles, if we know the volume and the molarity, we just times those things together. So we have 0.100 molar NaOH, so moles per liter of NaOH. And if we times that by the volume, and I'll convert to liters here. So I'm going to erase this picture. It's kind of in my way. So if I do that, I just move the decimal one place over. So I must have 0.00250 moles of NaOH. Squeeze it in there. Okay, so I know that's how many moles I added to reach this thing they call equivalence point. So I added that many moles at the base. So what I'm trying to find out is this connection here between OH and H plus. So if I add that much NaOH, I should be able to figure out how much OH I added. So the moles of OH that I added would have to be equal to the moles of the NaOH, because every one NaOH would produce one OH. So the moles of OH minus would equal the moles of NaOH, which is that number basically. So I'm not going to rewrite it out, just being lazy here. And now what I know is that if I have reached equivalence, which I was told I did, I reached equivalence, then the moles of H plus have to equal the moles of OH, because that's the definition of the equivalence point. So the equivalence point, or equivalence, is when the moles of H plus equal the moles of OH. So basically, that calculation you did at the very beginning right there, that's the same number. So that's the number of NaOH, which is the number of OH, which is also now the number of H plus. So now what we want to find out is the moles of the acid. Now you do have to be a little bit careful with this calculation because it depends on the acid you have. But this acid is a monoprotic acid, which means that for every one acid, you only have one H. So the moles of the HCl must also equal the moles of the H plus. Once again, all going back to this very first number you calculated. So the actual mathematics is pretty simple, but I guess conceptually it's a bit trickier because you're trying to link all these concepts together. So this is kind of just understanding that for every NaOH, there's one OH. For every H plus, there's one OH minus at equivalence. And for every one HCl, there's one H plus. So now what we're trying to find out is the actual question, which is the concentration of the acid. So we know that the concentration of any chemical is the number of moles divided by the volume of that chemical. So we know the number of moles is what we worked out up here, which was 0.00250 moles. And now comes the tricky bit, which is what volume do you actually use here? If you watched yesterday's video, those questions, you had to find the combined volume because you were mixing two different chemicals together. And if you haven't watched the video, make sure you go back and watch that. And so the question now becomes, what number do you think you would put down here? Well, you have to figure out where did you do the titration? What was the volume of the acid you actually titrated? And so remember at the very beginning, we said you had 250 mils and you took a 25 mil sample to titrate. So you have to be careful which number you use here because you didn't titrate all of the acid. You only titrated a sample. So down here, we're going to be using the 25 mil sample here. So I need to divide this by that number of liters, so 0.0250 liters. Is that okay? So we work that out. So we're going to go 0.0025 divided by 0.025, just a one movement of a decimal place. And we're going to be getting 0.100 molar acid here. So let's see if that makes sense. So we're going to just double check my math here. 25 divided by 0.025. So I'm getting 0.1. Let's see if this kind of makes sense here. So I'm going to take a look at what we started with. So we basically, we had, oh, actually, sorry, my bad. Oh, my bad. So bad. Sorry, guys. Let's try that again. So base. We use 35 mils of base. So here, this should have been 0.0350 liters, which means that should have been a 3 there. And we go through the work here, which means this down here, this would have been a 3 right here. So we work that out again. So 0.0035 divide by 0.025 is equal to 0.140. So let's just go back and once again check to see how we could have caught that mistake. So up here, it says that you have a 0.1 molar solution of base, and you use that much base, 35 mils, to titrate only 25 mils. So the concentration of the acid has to be more than the concentration of the base, because if it was the same concentration, you would have had to use only 25 mils of base. So you actually had to use more base than acid to neutralize it, which means that the acid must have been a higher concentration. So this kind of question, if you look at the math, unless you make goofy mistakes like I just made there, this, writing the wrong number down, what you'll notice is that there's really only two calculations. You find the concentration and then times it by the volume to get the moles of the base. And then basically you just go moles of OH, moles of H plus, moles of acid. And then you have your HCl concentration, which is the number of moles of HCl you had divided by the volume that you actually titrated. So even though you have a small glass here, it's 25 mils, the concentration here, this number here, would be the same concentration in the original beaker. And so that 250 mils could now be used, I guess minus 25, could now be used for other experiments that you want to work with. So I'm going to give you a different question here and see if you guys can work through the math of it. There's a little twist to the question. See if you catch it here. So let's say example, you titrate 30.0 milliliters of H2S, and equivalence is reached when, let's say, 17.5 mils of 0.200 molar KOH is used. So when you guys try that question, once again, use the steps above, and there's a little step you have to worry about here. But let's see what you would do. I'll give you maybe a couple minutes, just maybe 2 minutes to try that. Okay, so the first thing we need to find out is the moles of the KOH that we use here, and so our base being potassium hydroxide. And to do that, we want to find out the volume of base we used, and also the molarity of that base. So if I sort of do the same thing as before, I would take 0.200 moles per liter and multiply it by a volume of 0.17 0.0175 liters, and that would give me 0.2 times 0.0175 0.00350 moles. Okay, moles. And now what I know is the moles of the OH would have to equal the moles of the KOH. It's a monoprotic base. And now I know the moles of H plus equal the moles of the OH, because I've reached the equivalence point. And now I got to try to make sense of the moles of the H2S. Okay. So you probably were aware that there's a 2 here, so that must change things here. So we have to figure out, should we double the number we got, or do we half the number, or square root? What other things can you do with a 2? Square it. So let's see what we would get here. Well, the connection is that we have, what I might write down is I have 0.00350 moles of KOH, which is also the same as the OH, which is also the same as the H plus. So that's really what I want to write here. And now what I know is that for every one H2S, there are 2 H pluses. So I need to divide this number by 2. So that means there should be half the amount of acid as there is H pluses. So I divide that number by 2, and I get 0.00175 moles of the H2S. So now to find the concentration of the H2S, I would take the number of moles, 175, and I would divide it by the volume of the H2S I use. Now, I used a slightly different setup here. I just basically said you took 30 mils of it. So there was no like original sample and then taking a portion of it. So 0.0300 liters. So I divide that by 0.03, and I'm getting a new concentration, or sorry, a concentration of 0.0583 molar. So once again, I'm just going to double check see if that makes sense. My acid, I needed more acid than I had base, and the base's concentration is 0.2. And I've almost doubled the amount of base here. But the acid's diprotic, so that makes it even more complicated. So you're looking like a factor of 4. So I think that's pretty close to what you would probably estimate it to be. So I hope that kind of makes sense. I did want to show you one other way to do this question, and I would say that if you're pretty good at math, if math's a pretty strong area for you, you might find this method easier, but it could be more confusing for some students. So I'm just going to label this as optional. But in university, you probably will work in these units. So I thought I would just show you this. So you'll notice in the first step of the calculation, I just times the volume and the molarities together, but I converted the volume to liters. And the reason I did that is because I had liters in the bottom of my molarity here, moles per liter. So you can see that if you multiply these numbers out, you might think to yourself, well, that's going to be a problem because this is in milliliters and this is in liters. But really, moles over liters would be the same as kiloliters over kilomoles over kilomole over kiloliters. It would also be the same though as millimoles over milliliters. So basically, as long as the prefixes are the same, they're the same. So I can actually times just by 17.25. So if I do that, 0.2 times 17.5, that gives me 3.5 equals 3.5. But now this would be 3.5 millimoles. Okay. And so when I go down through the calculations here, I would still divide it by 2 because at this stage here, I would have 3.5 millimoles of H plus, and then timesing it by a 1:2 ratio, which would still give me, so divide that by 2, and that would give me 1.75. Now it'd be millimoles of H2S. And now if I want to find the concentration of the H2S, I just got to remember though that because I'm working in millimoles, 1.75 millimoles, I would now divide it by 30 milliliters. And then you get the same number at the end here. So I'm just gonna say optional here. You don't need to do it that way. I just find that some students, when they go to university, that's kind of what they see. So if you want to work in those units, you can. But I think a lot of students would be more comfortable just using this approach here, which I'm totally understand. So I was going to just do one more thing here. It's not going to be a full question though. Is if you have your book handy, and you turn to page 154 in your book, 154. And you just kind of flip through all the way to about page 157. So like 3 pages there. You're going to see a bunch of different types of problems involving titrations. And normally I would have covered all of these for you guys. And I would encourage you, if you are going into post-secondary, that you do look through them. But as far as testing you on them, I'm going to test you on the ones that I've just shown you, this concept of the ones I've just shown you, finding the concentration of an unknown chemical. And I'm also going to test you on sort of more of an experimental part, a procedural part that you would want to do. And that's going to involve multiple titrations. And the reason I want to do that is in a lab, this is really what you would do. So I'm going to go through just the setup of this so you can sort of see what I'm talking about here. But this concept is covered at the bottom of page 157. And it talks about experimental notes. And I wanted to cover this because if you actually go to university and you do a titration, you say, okay, I got my beaker, I'm holding it below the burette, I've added my chemical, I've reached the equivalence point, here's the concentration of the acid. Your lab instructor is going to laugh at you and say to you something like, you just did it once. And you're like, yeah. And they're saying, why would you do that? How do you know you're right? So what you actually do is when you do a titration, you have your burette with your stopcock, and you pour some base into your acid, okay? And then you kind of get the results you got above here. But like many things in science, you need to conduct multiple experiments to sort of verify that your number is even right. So what you might do is you might repeat the experiment again and again and again. I'm getting tired of drawing these, and again. And basically what you're looking for is, when does your data start to sort of suggest a similar amount? So what we want to do here is we want to make sure all the conditions are the same. So you want to make sure that your standard solution is the same standard solution in all experiments. And then what you want to really make sure of is the sample that you're titrating always comes from the same source. So it needs to be the same sample. But what's even more important, it has to be the same volume. Well, you probably could do some calculations around that, but it has to be the same sample. So you titrate it multiple times. And what you might find is maybe the very first, I'm going to write a little chart here. The first time you test it, let's say volume of base. I might say volume of standard. You may actually you could actually do a reverse experiment where the standard is an acid and you're titrating a base you don't know the concentration of. But let's say the volume of the standard. And the first time you do it, let's say you get 22.35 milliliters of base being added. And that's when you reach equivalence point. So add it to reach equivalence point. Okay, and then you do the experiment again. So this is like trial 1. And in trial 2, you do it again. And this time it takes you, it's 20.01 mils to reach the equivalence point. So you're using the same standards, same samples, and you're kind of saying to yourself, well, hang on a second, these numbers are different, right? They're obviously different. And you might say, well, human error, maybe you just wasn't very accurate. You turned the stopcock too much or too little, and you got a different number here. So he's like, well, which is the right number? Well, I'm going to probably need to do it again. And let's say you now get a number of, say, 19.89 milliliters. Okay. So this is number 3. And you're thinking to yourself, well, it looks much closer to the second one, even though it's a 19. It's only separated by 0.11 units. So maybe I'll do it again. I'll do a 4th example, 4th trial. And this time you get, let's say 20.02. Oh. Yes, Noah, you asked a good question. I'm gonna come back to that in just a second, okay? So Noah's question was, how do you know when equivalence is reached? So that's a really good question. So give me a second just to finish this off here. Okay, so let's say you're looking at these 4 trials you did, and what you're trying to find out which of these numbers do you use to do that calculation? Like which number do you use for that? Well, if the numbers are close, we'll talk about what that means in a second here, but if they're close, you use those numbers. But if the numbers are off, then you have to exclude that value. So when I look at these numbers, these 3 are all fairly close, but the first number is quite off. It's over 2 milliliters difference, which is quite a bit of difference here. And so we would exclude that number. We'll talk about why that might happen. So then what you do is you average you would average these three numbers. So if I do that on my calculator, so 20.01 plus 19.89 plus 20.02, and I divide that by 2. No, I don't times that by 2. Divide that by 3. Then I get an average number of 19.97-ish, around there. So that's the number you actually would use as milliliters, of course. So that's the number you would use for your volume of base required. So I hope that kind of makes sense. That's sort of an averaging of those numbers. So you might say to yourself, well, what do you mean by close? Because I mean, that's all perspective, right? And so generally the rule goes is somewhere between, if the numbers differ by about plus or minus 0.02 mils to about plus or minus 0.1 mil. So if the numbers are within that margin, then we generally accept them. And so in high school level, we kind of generally go with that. And the reason being, usually what happens, and this actually kind of leads into Noah's question, is you're looking for the equivalence point to happen. So you're actually turning this knob here, adding base, and you're waiting for this thing to say, oh yeah, now we're there. And you might, what we call, overshoot the mark. Like you basically add too much of the chemical in, or too little sometimes. And so you want to do multiple experiments and then average those volumes out. So you'll see homework questions where they give you multiple volumes, and all they're trying to get you to do is exclude the one that doesn't seem to fit the data, if that's true, and then you would average them out. If the first one though had been like 20.02, then you would have included it. Now you would have added the 4 numbers and divided by 4. And so this is just a way for you to feel sort of assured that you actually have reached a good number for the equivalence point. Because what you're trying to establish is, when do the moles of H plus equal the moles of OH? And for this question, that would be the volume when that happens. So hopefully that makes sense. And it's going to deal with Noah's question here, which is a good question, which is, how do you actually know that you've reached equivalence? Like what would you be looking for? Like, would the solution just say to you, stop? And how would you know that? Well, generally what we do is we add a chemical referred to as an indicator. And I would have shown you all this in class, and it's so hard to teach this because it's not as exciting when you're just looking at a video presentation. But an indicator basically is a chemical that changes color at different pHs. So if you have an acid in your beaker, it has a very low pH. And so the indicator in that beaker would be a certain color. So your solution might look green or something like that. And then when you add a base, you start neutralizing the acids. The pH goes higher and higher, and eventually it would change color. The indicator we tend to use, and you'll probably see this written in some of the questions, is a tough one to say, especially if you have a speech impediment. Phenolphthalein. Phenolphthalein. Not sure who thought of that word up. So phenolphthalein. So it's an indicator that's colorless. So it has no color. So it just looks like a glass of water at 1 pH. And then at a certain pH, it changes to pink. So basically, it goes from being colorless to pink. So going back to Noah's question, which was, how would you know when to stop? Well, you'd be adding your base, and the solution would initially be colorless, and all of a sudden it would turn pink. And what you really want to get is the lightest shade of pink. So if you keep adding, it gets darker pink. And so if it's really dark pink, then you've gone too far. So probably what you would have seen up here, if you did this experiment, is if you added that much base, the solution would have been really, really pink. But if you added this much base, you would see like a really light shade of pink forming, and that would alert you to stop at that place. So we actually use indicators to tell us when to stop doing the titration. So I'm going to just switch back. I'm going to go back here. I'm going to stop recording. And so if anyone has any questions they want to ask, let me just stop this recording.